Okay, so these are the notes that we should be on today. We are talking about tests for population mean. There's actually two parts to this section. One is about the actual hypothesis tests, and then we will talk about something called power. I don't think we're going to get to both. I think we'll just get to the hypothesis test part. Like I said, because you've talked about this, I'm going to try to be efficient to talk about the background and then how to use the calculator. 3 conditions for conducting a significance test for population mean. Okay, let's talk about a confidence interval for mean. Confidence interval for mean, what is the first assumption? First assumption no matter what, always. What is it? Random sample. Second assumption? Augie? Approximately normal sampling distribution. And then the third one is the 10% rule. Sample size has to be less than 10% of the population. Few things to say here. 10% rule, remember, is only when we're sampling. So in the case of an experiment with volunteers, we don't need to do the 10% rule. We have volunteers. We didn't sample. And then that second assumption. For mean, this one is a little bit trickier to check because there are 3 different ways. For proportion, we've talked about it's either n times p hat or n times p. But mean is the one that is a little trickier. First option, either the population is normal, or we're using the central limit theorem. And what is our last option? Can we be more specific than calculator? Graph of the sample. Okay, all of those are for a confidence interval for mean. So we need to talk about what are the conditions for a hypothesis test or a significance test. Guess what? They're exactly the same. Exactly the same. So nothing new, you're checking the same assumptions. Okay, talking about a test statistic. So for proportion, it was z equals. And that goes back to the confidence interval formula, which has z in it. If we think of mean, the confidence interval formula does not have z. What does it have instead? T, right? The confidence interval formula for mean, if we look at both of them, proportion is p hat plus or minus z times the square root of p hat, 1 minus p hat, all over n. But then for mean, it was x bar plus or minus t times the standard deviation over root n. So test statistic for proportion uses z. Test statistic for mean is going to use t. So it will be t equals. And if you remember from before, the formula is not on the formula sheet. It's in words. It says parameter. Nope. It says statistic. Subtract parameter. All over standard error. So all we have to do is be able to take those words, put them into symbols. So the statistic for mean is sample mean. The parameter is population mean. And then the standard error, that's on the formula sheet, or it's just directly from the confidence interval formula. So it's S over root n. So we're going to get a t value, but then we're going to have to find a probability with that t value. So with proportion, we found a z value, and then we used the normal distribution. So the question is, what is a t distribution? Because t is not the same as z, and it is not a normal distribution. So before we look at calculating that probability, I want us to make sure that we know the basics of a t distribution. So if we talk about the shape of a t distribution, it is a symmetric distribution, but it's not quite normal. And that is because it is more spread out. So So it's a symmetric distribution that looks normal, but it's actually a little bit more spread out than a normal distribution. The center of the t distribution is 0. That's a standardized distribution. Just like the z distribution, z-scores also has a center of 0. And this is the one that is really important, is talking about the spread. So the spread of a t distribution. The t distribution is more spread than the standard normal. Standard normal is z. But it gets closer and closer to normal, or to z, as the degrees of freedom increases. So that df, just remember, is degrees of freedom. That should sound kind of familiar. If you remember the t table, when we were looking up our t and z values on the table, do you remember talking about how z was all the way at the bottom with that infinity? So as the degrees of freedom is going up, we get closer and closer to normal. Infinite degrees of freedom is the normal curve. So t will become z. Okay. Questions on that before we do some calculator stuff? Okay. Calculating a p-value, it's very similar, so we're just going to jump right to these examples down here. So our test statistic, like we wrote on the previous page, x bar, subtract mean, s over root n. So we are calculating the test statistic and the p-value for these two examples. For the first one, if we do t equals, our sample mean is 9.7. So we have 9.7 subtract. Mu is just the null value, so that's 10. And then we're going to divide by 2.1 over the square root of 35. And if you trust me, you get about negative 0.845. I do want you to do this next part with me. Okay. We have a lower tailed test. So we're looking for the probability that t is less than or equal to that negative 0.845. Okay. When we did z, so when you were doing the proportion examples and you were finding the p-value, where did you go on the calculator? You just did this in your homework. Where did you go on the calculator when you had your z value to find the probability? Normal CDF? Okay, so right now hit second distribution again. It's not normal CDF this time though. So hit second distribution and you should find a T CDF. So it looks like maybe it's number 6, T CDF. And it should look pretty similar. It's going to ask you for lower bound, upper bound, degrees of freedom. Lower bound, upper bound, degrees of freedom. So we would do T CDF. Our lower bound is some really big negative number, all the way up to negative 0.845. What do you think the degrees of freedom is here? Same as it was before. How do we figure out degrees of freedom? N minus 1. So 34 degrees of freedom. Okay, and if you do all of that, I believe you get 0.202. You guys agree? Okay. questions for me? Okay, I would like you to take a minute and do part B, please. So take a minute and do part B. Let's come back together. It seems like we're having some issues figuring out what to put in the calculator in terms of direction. So a lot of us, I heard and saw, got the right test statistic. A lot of us knew to double our answer. But then the issue is that many of us got a probability that was bigger than 1. And we noticed that and said, oh, something went wrong, which is great. Okay, so the way to figure out that this should be greater than is you have to picture your figure. Here's the center. Here is the value that we got, 3.107, because remember the center is 0. If it is a two-tailed test, you are always shading away from the center. More unusual from the center. So in this case, from 3.1, that would be bigger. We double it then to get the other tail.
What would be a case where you would do lower bound? Like what kind of number?
If it was negative 3.107,
Okay.
then you're going to go down.
Okay.
It seems like this would be a great time for me to show you how to do it on the calculator so that you can check your answer. Yeah? Maybe that would be a good idea. Because it's hard for me to show the calculator up here, I'm just going to talk you through the steps right now. I'll write them down, but I'm not going to bring up the calculator. Okay, you can probably guess. You're going to hit stat. And you're going to go over to tests. We're doing a test for mean. So we've said in the calculator will always say proportion, but it won't say mean. So the one that's for mean is just plain old t-test. And then you have data versus stats. Right here, we do not have the raw data, we just have the statistics. So you will choose stats. And then it's going to ask you to put in the null, which is 85. It's going to ask you for the sample mean, which is 93, the standard deviation, the n-value, and then you could choose its two-tailed test. When you go to calculate, you should get this same p-value that we got of 0.0072. Do you? Okay, like before, this is only a way to check your answer. So I do not want us using this to do all of the calculations. I want us showing the work like we did in A and B, including a figure, and then go back and use the calculator to check your answer. Okay, we're going to do an example. You are skipping the next page that has all the numbers and says something about Abby and Raquel. And you're going to this page, the children's game, Don't Break the Ice. Have you guys ever seen this game?
Yes.
Okay. In the children's game, Don't Break the Ice, small plastic ice cubes are squeezed into a square frame. Each child takes turns tapping out a cube of ice with a plastic hammer, hoping that the remaining cubes don't collapse. For the game to work correctly, the cubes must be big enough so that they hold each other in place in the plastic frame, but not so big that they are difficult to tap out. The machine that produces the plastic cubes is designed to make cubes that are 29.5 millimeters wide, but the actual width varies a little. To ensure that the machine is working well, a supervisor inspects a random sample of 50 cubes every hour and measures their width. That output at the side, that's called Fathom, the software for stats, summarizes the data from a sample taken during 1 hour. Okay, so you're going to notice there are 4 different numbers here, and then Fathom below tells you what each of them are. So the top number is the sample mean, it was a sample size 50, and then we have the standard deviation and the standard error. Before we actually do the test in part A, we're going to review how do you interpret standard deviation and how do you interpret standard error. Standard deviation is just the typical deviation from the mean. So if I do that in context, I'm going to say typically observations in cube width deviate by 0.09 millimeters from the mean. So that's the standard deviation. We've interpreted that before. Standard error on the other side, on the other hand rather, that is our standard deviation divided by root n. That is a measurement of standard deviation also, but it's a measurement of standard deviation for the sample means. Like if we were to take a whole bunch of sample means, it's how far those would deviate from the population mean. So in words, typically, sample mean widths of size 50, so samples of size 50, deviate by 0.013 millimeters from the population mean width. Okay. Part B, do these data give convincing evidence? Okay, I was asked about the homework. I was asked about this in your homework. Do the data provide convincing evidence? That is asking you for a full hypothesis test, all 4 C's. So it then even says use a significance test. It won't always, but if it says, is there convincing evidence, you're doing a full hypothesis test. So we will start with choose. So this is a test for mean. So we're going to have mu equals. Okay, so we want to know, is the mean width of the cubes produced this hour not 29.5? So our null, we're assuming that the population mean is 29.5. We are looking for evidence that it's not 29.5. And we need to define mu. So mu is the population, or you can say true, either one. Population or true mean width of cubes produced this hour. But then we need to say we are carrying out a hypothesis test. So what we need to say is carry out a two-tailed, one sample hypothesis test for mean using alpha is 0.05, and then we're going to be using t with, if it's a sample size of 50, it's going to be 49 degrees of freedom. Again, I don't care what order you put all of those in, as long as you put all of them there. The most common thing that people leave off is they forget to say the word mean. So that is the most common one that people forget. Okay, now that we've made our choice, we have to check our assumptions. First one, do we have a random sample? It says a supervisor inspects a random sample of 50 cubes. So yes, that is stated. Secondly, do we have an approximately normal sampling distribution? Remember, you have to say sampling. Please do not just say normal distribution, because there's 3 different kinds of distributions. I need to know that it's sampling. What is the first way to check this? population would be normal. That would be stated. It's not. What's the second way? Central limit theorem. Look how convenient. We have a sample size of 50. So we can say yes by the central limit theorem. And I do want to see in parentheses that 50 is bigger than 30. That's why we know that the central limit theorem applies. Thirdly, we are sampling, so we need to know, is our sample size less than 10% of the population? So is 50 less than 10% of the population? So is n bigger than 500? I don't know. I think that's reasonable. So we're going to say yes. Reasonable to believe. Is it a machine? Yes. This machine makes more than 500 cubes in an hour. Okay. Now we are finally on to the calculation step. So our formula, x bar, subtract the mean over the standard error. X bar and S are higher up in the Fathom output. I'm not going to move the page, but I'm going to pull the numbers from there. So when you see these numbers appear, that's where they came from. The sample mean we were given is 29.4846. That mu comes from the null, so that's 29.5. The standard deviation was 0.09, and we're dividing by the square root of 50. We already know what this value is going to end up being. That's the standard error. So we also could have just put 0.013 because we already know the standard error. This ends up being about negative 1.21. Okay, at this point, I'm going to go to the figure. So if I draw myself my curve, bless you, I have mean, standard deviation, 2 standard deviations, -1, -2. There's only 2 other things I want labeled on here. Label the null, so 29.5, and then label your test statistic. So 1 standard deviation away is -1, -2 standard deviations away is -2. So -1.21 is about here, -1.21. Which way am I shading? If it's a two-tailed test, which way am I going to shade here? Left or right? Left. So we're going to shade away from the center, but then we're also going to acknowledge that we have the same area on the right side. Okay, I'm going to write an inequality. If you want to write this, great. You do not have to. As long as you have that figure labeled and shaded, that is perfectly fine. So on the calculator, we are looking for the probability that t is less than or equal to -1.21. But then we're going to double our answer for the 2 sides, using, of course, 49 degrees of freedom. Can you guys do that real quick, please? I believe you get 0.2322, about. And you could use the calculator to check it to make sure that that's the correct p-value. So again, that inequality in green, you do not need to show if you have a figure that is labeled in shade. We okay so far? Okay, so what is going to be our decision here? What's our decision for the test? Reject or fail to reject? Fail to reject. Okay, it is so very important that you take that p-value and you show that it is bigger than 0.05 because that's why we fail to reject. You have to show that.
Do we not have to interpret the p-value?
Oh no, we're going to also. Don't you worry. It's part of our conclusion. Okay, so I fail to reject the null. Okay, I'm going to stop there. I'm going to talk, then I will continue writing. If we fail to reject the null, that does not mean we believe the null. It does not mean we accept the null. All that it means is there's not enough evidence for the alternative. So that's what we need to put in words. I fail to reject the null as there is insufficient evidence that the population mean width of the cubes produced this hour is not 29.5 millimeters. All I did was copy that word for word from the question. So a few people have asked me then, I know we need to answer the question, do I need to write another sentence? In this case, no. This directly answers the question. Does this mean that the machine is working properly? Like, can we say definitively we know the machine's working properly? No. I want to be clear on that. We do not know without a doubt that the machine is working properly. As Alex reminded us, we are also going to interpret the p-value. Okay, assuming the true mean cube width is 29.5 millimeters. 0.2322 is the probability of a sample mean of 29.4846 millimeters or more extreme by chance alone. Every time you write a conclusion, I'm going to have you write that sentence. Veronica?
If it's just a one-tailed test, then do we say like the value or greater than or less than?
You can. You can also say more extreme.
Okay.
It's just not as specific. Okay. Questions? If you notice, there's a part C. Part C asks us to calculate a 95% confidence interval and wants to know, does the confidence interval support the decision from B? I'm not having us do the whole process. Okay? What I am going to do, though, is we're going to pause. You're going to get together in your group. All I want are the numbers and the calculation for the confidence interval. So just the calculation step. So you're going to take 5 minutes in your group, construct that confidence interval, and then I just want yes or no, does it support what we just did in this test. You will probably have to look back in your notes unless you just have that right off the top of your head. So, good luck. We'll come back together in 5 minutes. Here is what I got in green. So here's our formula. We should be using 49 degrees of freedom. You could either round down to 40 or use 50 since 50 is so close. This is from the table, that 2.021. So this is the interval I got. I think if you used 50 degrees of freedom, it should still be pretty close. Okay, so then, lastly, does the interval support the fact that we failed to reject the null? Yes, Alex, why?
Because the value of 29.5 is in the confidence interval.
Exactly. What we care about is that 29.5 is in the interval. Again, like we said, that does not mean the machine is working properly. It means it's possible the machine is working properly. We do not know that for sure. Did that go okay? I have one more thing I want to write down, and then we will take our second break. Sound good? Okay. I would like you to go back to the previous page, the one about Abby and Raquel that we skipped. So I want you to take a look at this one. We are not doing the whole test. All I want to discuss real quick is for the assumptions or the check part. We would still have the random sample. We would still have the approximately normal. And we would still have the 10% rule. I want to talk about the approximately normal though. Okay, so in this case, we have 24 observations. That's all we know. We're not told the population's normal. We can't use the central limit theorem. So if you were going to check this approximately normal, what would you have to do? More specifically? A box plot of the sample. I'm going to draw the box plot and we're going to write a sentence. That's it, because I want to make sure that we write the sentence correctly. If you trust me, the box plot looks kind of close to this. And what we would say is, because the sample does not show extreme skewness, there's skewness for sure, but it's not extreme, or outliers, the sampling distribution is approximately normal. I will be very picky on this word sample and this word sampling. And then of course the last option would be the population is normal. You had that on your test, so you would need to very specifically write the population is normal, so the sampling distribution is normal. One more thing I want to write down. Last thing, and then I promise you we're moving on. The central limit theorem is for mean only. To check normality for proportion, what would you have to do? n times p, and n times 1 minus p. So central limit theorem should not come up on your quiz this week at all, because your quiz does not have mean on it. So please don't use central limit theorem. The only way for proportion is n times p. And remember, you don't even have to show np. All you have to show is the numbers. And show that they give you a product that's greater than 10. Questions from me before break 2?